Welcome to the class of Principles of Communication. In previous classes, we have discussed symbol timing recovery using cluster variance minimization, output power maximization, and early late gate method. In this video, we will learn other practical methods for symbol timing synchronization through Matlab examples. Symbol timing synchronization is to find optimal instant when downsampling a sequence of received samples into received symbols. At the communication receiver, the received signal goes through the matched filter and then sampled at the symbol period. Because of symbol timing error, we may not sample at the best point. The timing error is detected and it becomes the input to a loop filter. The loop filter is an interpolator and a proportion controller so that the output is in a timing offset, then adjust the sampler, make sampler sample at the best position. If the timing error is 0, then the loop filter is locked, so we are locked to the best sampling position. If the timing error is non-zero, and then this value will adjust or control the loop filter, make this output offset vary. The idea is very similar to previous loop filter for phase synchronization, the phase lock loop. Here is the same idea that we have this online loop that we detect some error, using that error message to control and offset the sampler. In this time, we are adjusting the timing for synchronization. Once the entire loop is locked, we achieved timing synchronization, the symbol timing synchronization. Now we want to check the value here at the output of timing error detector. If this value from the timing error detector is 0, that should mean that the sampler is perfectly synced, timing synced. If the output of the timing detector is non-zero, then the loop filter should output a non-zero, positive, negative tau, the non-zero timing offset accordingly. Let's see if we can check this feature of this loop using Matlab. In the Matlab program, let's first design a squared root raised cosine filter for post shaping. The raised cosine has an oversampling factor of 8, L equal to 8, with the rollout factor beta equal to 0.5, and the span of the filter is 10 symbol period. Therefore, altogether I will have a coefficient 10 times 8 plus 1, 81 coefficients. On line 10, I designed the transmit filter. That's a root raised cosine with the rollout factor, with the raised cosine span, and the oversampling factor. On line 11, I defined the received filter. We can see that is the matched filter because I take the transmit post-shaping filter and flip the order, then complex conjugate, though that is a matched filter. On figure 1, we plot the transmit filter. On figure 2, we plot the receive filter. Because it's a raised cosine, it's symmetric, so we should see these filters are exactly the same. Then on figure 3, we are going to plot combined transmit receiver filter. So this filter is a convolution between the transmit post-shaping filter and the receive matched filter. And that should be a raised cosine. We plot this with the amplitude. In addition, we want to highlight the zero crossing of the raised cosine. Therefore, line 34, we are defining a zero crossing vector with all non-applicable variables. Then line 35, we particularly insert all these L-spaced zero crossing samples with zeros, and then draw that on the same plot. Let's run this portion. Now here we have the result. Figure 1 is the transmitter filter. That's a loop raised cosine. Figure 2 is the received matched filter. It is also a loop raised cosine. That is exactly the same as the transmitter filter. Figure 3 is the raised cosine. That's a combined filter. With all these red dots, those are the zero crossing point. That means if my filter is a Nyquist filter, as we know from the previous chapter, then these other symbols, the neighboring symbols, will be exactly at the zero crossing points. Then we work the symbols at the transmitter side. We are using a two-pan modulation. And on line 47-48, we define the data. The data has a length as 2 times the raised cosine span, or plus 1. And the symbol sequence is a binary sequence. The symbol sequence we generate here has a very unique pattern of 1, -1, 1, -1s. On line 51, we call Matlab modulation a pan modulation with the symbol data and using 2 pan, m equal to 2. On figure 4, we plot the transmit symbols. Then we upsampling the transmit symbols with upsampling rate L equal to 8. Upsampling is just simply padding zeros in between. On figure 5, we plot out the transmit upsampling sequence. The upsampling transmit sequence will go through the post-shaping filter. So line 69, the transmit sequence is filtering of the upsampling sequence with the transmit filter, which is the raised cosine. On figure 6, we plot the transmit sequence. So let's run this portion of the code. Okay. So we see here on figure 4, indeed, we have all these binary symbols that gives us 1 and a -1. On figure 5, we have the upsampled sequence with all these zeros in padding in between those 1 and -1s. Figure 6 gives us the transmitter symbol, that is the symbol convolved with the square root raised cosine. Next, we add a channel effect. This channel is a simple propagation delay with a time offset. We arbitrarily choose and add three samples. So the received signal is a delayed signal that has this time offset, which is 3 sample delay. We execute this portion. At the receiver, we filter the received signal, the delayed version of the received signal, with the received filter, which is the square root raised cosine. So MF output is this matched filter output. On figure 7, we plot out this matched filter output. Then on line 95, suppose we have symbol timing synchronization is perfectly done. So I can downsample the matched filter output with a downsampling rate of L equal to 8. Time offset is 3 sample. Suppose we already know that. So it's a perfect situation. Because we want to show the sampled positions on the same plot, on line 98, we upsample the symbol again using the upsampling rate L equal to 8. Then this is upsampling, then we padding zeros in between. Now at this time, suppose we have perfect timing sync, so I know the time offset. So I'm putting the time offset with my timing phase in the upsample. Then line 99 is whenever I have those zeros, those are in padded zeros, and then I give a value of not applicable. So it is not going to show on any plot. On figure 8, I plot out the matched filter output, and on the same plot, we plot the selected sample which is the red lines, red dotted lines of the picked samples. On figure 9, we plot the received symbols. These are the received symbols that we extract from the samples. These are the symbols that go through the symbol detector. On figure 10, we also plot the constellation of the symbols. Because this is a 2-pan, it is also a scatter plot, so I only have two values, positive 1 and a negative 1, on the complex IQ plane. I stands for in phase, Q is the quadrature, so that is the constellation 2D plane. Now let's run this portion of the code. Okay. On figure 7, we see the output of the matched filter. So this is the output of going through the whole raised cosine. On figure 8, we have the red dotted line. Those are the downsampled sequence. These are downsampled sequence that sampled at the perfect position. Because we have timing synchronization done, I know exactly the time offset. We can see those red dots are exactly sampled at the best position, give me positive 1 and negative 1s. Now this position here, because I have some filter effect, or the head of the filter or tail of the filter has some filter effect, but we know we indeed sample at the best position, give me a perfect 1. And if you can see these points are zero crossing points. And figure 9 are the extracted symbols. So we extract those sampled value. These are exactly positive 1 and a negative 1s. And on figure 10, we can see the constellation. That is a perfect constellation. Give me those symbols on 2 points, positive 1 and a negative 1, for very easy detection. Now let's see what will happen if I don't have perfect timing synchronization. So I will change here with without the known timing offset. So we just simply sampled at 0, L, 2L, 3L at those sample points. And I also need to remove this. So let me write this here. So remove this part to represent exactly the position that I sampled. Let me rerun this part. Okay, so figure 7, this is output of the matched filter. Figure 8, now this is the matched filter output with the downsampled sequence, which is the extracted symbols. We can see all these red dots, they are not perfectly sampled. They are sampled at the offset, with offset negative 3, of course. And these numbers are very small compared to the real symbol positive 1 and negative 1. Then figure 9 is the extracted symbol. And we see these values are relatively small compared with what it should be, positive 1 and negative 1. Then figure 10 is the constellation. Now this constellation has some error effects. It should be perfectly on positions positive 1 and a negative 1. However, these symbols, because of timing errors, they are shrink. They are moving toward this boundary. Now if I'm adding more noise, that will give me some problems at a detection time. So how to find these perfect timing offset? Now in this example, we know I want to sample at this peak, at this peak, this peak, and this peak for my special choice of the sequence, that is positive 1 and negative 1. These peaks represent the best sampling position or sampling offset that gives me perfect symbol positive 1, negative 1, and positive 1, negative 1s. So my thought is that if I take a derivative of this waveform, of this oversampled waveform, and the derivative at those peaks should give me zeros. Those are the best position I can get for sampling. And if I input the derivative of this output to my timing error detector, and a 0 stands for a locked position. That means I have a perfect timing offset. On the other hand, if I have non-zero values of the derivative, that means I have not reached this peak position. So I do have some input to the loop filter, and then the loop filter will generate a positive or negative tau, that is the timing offset adjustment. So we see that here, I really want to find these positions at those peaks. If I can take a derivative of my received samples, I want to find the derivative of this point of dx dt equal to 0, and that will be the best position to sample. Now, how to find a derivative or to program a derivative? In digital signal processing, we know we can do something that's simpler. So if I'm taking the difference of two consecutive samples, and this difference is equivalent to a derivative in the continuous time domain. So I can use that as the derivative. Now, using the difference, that's a usual practice in digital signal processing. We use that difference equation to replace a differential equation. We use a lot of that. But in here, if I'm using this difference, which is a simple difference between those two consecutive samples, I will generate a lot of high frequency noise. I will amplify the high frequency noise, which we don't like. So we are using some alternative method to find a derivative. So the derivative now we are using is using xn subtract xn minus 2 over 2. So instead of using a first difference differentiator, we are using this so-called central difference differentiator. Central difference differentiator, because the sample position xn minus 1 is not changing, but I'm taking two neighbor positions xn and xn minus 2, those two neighbor samples. It is equivalent that we are taking the sequence of x convolved with a filter, convolves with a filter h, and the filter h takes three values, that is half, 0, and negative half. In the Matlab program, we see that on line 131, that the filter, the central difference filter is h equal to 0.50 and negative 0.5. Then we convolve this filter with squared root raised cosine, and that gives me a central difference matched filter. On line 135, we removed the filter effect. So the filter length has a filter length of h. So 3 minus 1, we have removed this filter length of 2. Then in figure 11, we plot both the received matched filter, that is the square root raised cosine, and the derivative matched filter on the same plot with the derivative matched filter showing in red. Let's run this portion of the code. So indeed, on this picture, we see that we have the matched filter, which is the blue curve. That's our matched filter. And then the red curve is the derivative matched filter. We see at the best position, meaning that the matched filter at those peaks, and the derivative matched filter is the zero crossing point. That will give me the derivative 0. So this is 0. And here at this point is also 0. Here is a 0. And here as the peak of the blue curve, and I have a 0 on the red. With the derivative matched filter, we can build a maximum likelihood timing error detector. So here we have on line 149, the DMF output, derivative matched filter output, is filtering of the derivative matched filter with the received delayed signal. In figure 12, we plot out the DMF output. That's the derivative matched output, matched filter output. Then we downsample this derivative matched filter output with a not synchronized, so simply we downsample with L. We also compare that with a downsampled version with perfect time offset known. So that is with sync. Then we plot these two downsampled signals in figure 13. Then we detect the symbols. We do the PAM demodulation. First work on the non-synchronized signal. So that's line 176. Then we work on a perfectly synchronized, timing synchronized signal. That is line 177. We detect those symbols using the PAM modulation. We find out the error. That is the timing error detector output. On line 183, that's the error of a symbol without synchronization. So we can see here is a product of the detected symbol with the derivative matched filter output of the downsampled data. Now, if I have a perfect synchronization, the second term, this should be 0, so the error should be 0. On line 184, we can see exactly that. As a matter of fact, with synchronization, the DMF downsampled output will be 0, and then you multiply by the detected symbol, that will give you a 0 error. In figure 14, we plot out those two error output, the non-synchronized error, compared with the synchronized, timing synchronized error, which should be 0, that is plotted in color red. So let us run this portion of the code. Okay. So we have here on figure 12, that is the derivative matched filter output. In figure 13, we see that is the downsampled DMF output. As we mentioned, if I have perfect symbol timing, this output should be 0 because that is the derivative matched filter output. So you add a peak, the derivative should give you 0. So we see that the red dots are exactly at the 0 position. Versus the blue dots. The blue dots is without any symbol timing sync. Therefore, the derivative is non-zero. We can see we have some non-zero derivative at around 0.35 and negative 0.35. In figure 14, we see the timing error. This is the maximum likelihood timing error detector. The timing error for perfect symbol timing sync, that is error zeros. Those are the red dots. If I don't have a good timing sync, the blue dots are the non-zero errors. We can use these non-zero timing errors to design the loop filter such that it will output an offset adjustment, timing offset adjustment, positive, negative, tau, to adjust the sampler. Now you probably will wonder, this is a very special case because I am having a very unique symbol sequence that is positive 1, negative 1, and positive 1, negative 1s. So I have a very nice peak here on each symbol. What if I have two symbols, two consecutive symbols, which are positive 1 and a positive 1? So it can be something like this. Or maybe it's filtered, it may look like that. Okay. Anyway, that will confuse with the peak. It may not be exactly on the peak, such that the derivative will be equal to 0. For a practical random symbol stream, the maximum likelihood time error detector output could be very noisy, and this noise is called the self-noise. When we encounter a random symbol sequence, a zero-crossing timing error detector can be very useful. So the zero-crossing timing error detector is catching the feature that those symbols, they will cross 0 at the middle point if I'm changing from a positive 1 to a negative 1. If I change from a negative 1 to a positive 1, I will also have this zero crossing point. Ideally, those zero crossing points should be the middle point of my perfect sample positions. Now what about these two? If it's +1 and a +1, so there is no zero crossing point here. The result should not affect the timing error detector output. In the Matlab example, we have in figure 5, that is the match filter output. We take a specific symbol span of 8 samples, arbitrary from the 31st to the 31st plus L. In figure 16, we plot another symbol, that is symbol span from the 39th sample to the 39 plus Lth sample. We take the middle point of symbols of my matched filter output. So the matched filter output, the middle point is at L/2 plus 1, that's a central point, with the sample period of L and all the way to the end. That is without any timing synchronization. With timing synchronization, on line 217, we have the L/2 plus 1, then plus time offset. So we sampled exactly the middle point between two symbols. Now, how do we differentiate these two cases? Case 1, I have a zero crossing point that is coming from +1 to -1. So it's a falling curve that crossing the zero. The second case is from -1 to +1, that is a rising curve that crossing zeros. To differentiate these two cases, we can use those two symbols. Let's say this is symbol K, this is symbol K plus 1, and this is symbol SK plus 2. So if I have the difference between these two consecutive symbols, if this difference is negative, then I know I have a rising curve. If this difference is positive, I have a falling curve. And using that, I can tell the difference between these two different cases and use that in building my timing detection output. Now, why do we need that? Because these two cases tell me whether my offset tau should be positive or negative. I need to have those two non-zero values that is around 0, but give me a very clear positive, negative direction. In the Matlab example, we have here, this is on line 220, that is the difference between the detected symbol of no synchronization and with synchronization. The diff in Matlab is the taking an array that you shift one element and then you find a difference. So it's the difference between two consecutive symbols. And we are padding 0, just make sure that the overall array has the same length. This is called the sign of the corrected picked sample with no synchronization and with synchronization. Then the zero crossing time error detect output is that I have the middle sample output times the sign of correction, which tell me whether I have a rising curve or falling curve. Now, if my middle sample is a zero crossing sample, then the output is 0. So that is a perfectly locked timing loop. I don't need to adjust any about my sampler. If I have non-zero values, then according to the sign here, I know where should I put the timing offset. Should I give a positive tau or negative tau? For the case of two consecutive ones, for this case of two consecutive ones, because in this case, my result of sk minus 1 subtract sk, the difference between these two consecutive symbols are 0, because I don't have any zero crossing points. Therefore, in the Matlab, we will see this term will be 0. As a result, there is no zero crossing time error detect output, and the output will be 0. That is not doing anything to the loop filter. Finally, in figure 7, we plot out the zero crossing time error detect output with no synchronization and with synchronization. Let's run this portion of the code. All right. So figure 15, that is a single span with 9 samples. That is L equal to A plus 1, 9 samples here. Now the middle point, ideally that should be a zero crossing point, but because I don't have timing sync yet, so I have a non-zero value, which should give me a negative value here. Figure 16, that is another single span of 9 samples. The middle point here, the middle point is a positive value. It is not zero crossing. So there is no perfect timing yet. If I have the timing synced, figure 17 is a comparison of those two cases. The blue curve, the blue samples, are the sampled data with no timing sync. Therefore, the zero crossing timing error detect output, which is the timing error, will give me a non-zero value. And in this case, we can see those are all positive because I have shifted one direction, whether positive tau or negative tau, and using that, I can adjust the loop filter. Once it's locked, then the red dot, this is the perfect timing. Perfect timing is achieved. Therefore, the zero crossing TED output will be all zeros. At that time, the output is 0. Therefore, the loop filter output will also be 0. There is no more timing adjustment needed. The characteristic of the zero crossing timing error detector can be used here, so that will also give me a valid timing error detect output to control the loop filter, generate an adjustment for the symbol sampler.